Okay, so let's take a look at another question. This question comes from the HSC 2023 Advanced Maths paper. This is question 24. So we're told a gardener wants to build a rectangular garden of area 50 meters squared against an existing wall as shown in the diagram. A concrete path of width 1 meter is to be built around the other three sides of the garden. Let x and y be the dimensions in meters of the outer rectangle as shown. Show that y is 50 divided by x minus 2 plus 1. Okay. Well, we know the area of the garden is 50. So this is just part A. This is our setup part. This is a calculus optimizations question, and there's usually a setup part. Sometimes you get marks for it, sometimes you don't. So we know this is 50 meters squared, and we know this is y, and we know this is x. But we also know that this is 1, and this is 1, and this is 1. Right, so we have a whole bunch of dimensions here that are useful in helping us calculate these values. The garden itself, let's say that it has particular dimensions. Let's call them alpha and beta, just for the purpose of demonstration. Let's say alpha is this length here, and beta is this length here. We know alpha times beta is 50. That is 50. Because that's the area of that small rectangle. But we also know that y is equal to alpha plus 1, and we also know that x is equal to beta plus 2. Beta plus 2. And if we multiply x and y, we find that x times y is equal to alpha plus 1 times beta plus 2. So we've got xy is alpha plus 1 times beta plus 2. If we expand everything on this right side, we get alpha times beta, which is the first one. Then we have plus 2 alpha. Then we have plus beta. Then we have plus 2. This is all equal to x times y. Now, this is not the expression we want, but we're starting to get reasonably close. We know that alpha times beta is equal to 50. And this also tells us that if we want to do individual substitutions, alpha is equal to 50 over beta, or beta is equal to 50 over alpha. We also have y in terms of alpha and x in terms of beta. So we could say alpha is equal to y minus 1, and beta is equal to x minus 2. So this becomes 50. So we've got xy is equal to 50. 2 alpha, well, we're going to replace alpha with y minus 1, plus 2 times y minus 1, plus beta, which we know is x minus 2, plus 2. So now this becomes xy is equal to 50 plus 2y minus 2 plus x minus 2 plus 2. Now this is nice because we have 2 minus 2's here. This is minus 4 plus 2. This is giving us a minus 2. There's a minus 2 in the expression we have in the question. So this method, even though it seems fairly long, this method is getting us what we want. So we've got xy is equal to 50, and then we have plus 2y plus x, all minus 2. And now we need to solve this for y equals. So what we're going to do is we're going to minus 2y from both sides. This is going to get us xy minus 2y is equal to 50 minus 2, which will be 48, plus x. We're going to factor. So we have y in front of x minus 2, and then this is going to be equal to 48 plus x. Divide both sides by x minus 2. X minus 2. This is going to give us y is equal to 48 plus x over x minus 2. And so now this is almost what we want, but we're not quite in the right form. We have an extra x in the numerator and we have an x minus 2 in the denominator. So we can rearrange this a little bit. We can make this 48 over x minus 2 plus x over x minus 2. And then what we can do is we can add 2 on x minus 2 and subtract 2 on x minus 2. If we add 2 to the first term, this gives us 50 over x minus 2. If we subtract 2 from the second term, this gives us x minus 2 over x minus 2. X minus 2 over x minus 2 is 1, so this is 50 on x minus 2 plus 1. And this is what we're asked to show. Now this is a reasonably long way of going about this particular question. You could have done it much faster, right? By saying that if x and y are the greater dimensions, 50 is equal to x minus 2 times y minus 1, and you wouldn't have needed to do the alpha and beta. You could have done that very quickly and it would have much less algebra, but this method also works, right? Sometimes the working will only have a long form, right? So this is a long form of the working that gets the answer, and it's just going to be worth 1 mark, right? Any amount of working you have that gets you the mark is going to be correct. So this is part A. Part B then asks us, find the value of x such that the area of the concrete path is a minimum. Show that your answer gives a minimum area. Okay, so we've just been told y is equal to 50 over x minus 2 plus 1. This is the height, or the upwards metric for the measurement of this particular yard. And so we need to think about this in terms of the area of the path and in terms of the area of the garden. So the area of the whole yard is y times x, the area of the garden bed is 50, so the area of the path is going to be the difference. So the path area will be x times y minus 50. Well, we've just found y as a function of x, so we can plug that in. This means the path as a function of x is going to be x times 50 over x minus 2 plus 1 minus 50. If we expand this, this gives me 50x over x minus 2 plus x minus 50. So this is the volume of the path, or the area of the path I should say, as a function of x. Now I need to differentiate this, set the derivative equal to 0 to find min or max. So I need dp dx. Dp dx will be a little bit tricky here because this we have to do as a quotient rule. So we've got u is 50x, v is x minus 2, u prime is 50, v prime is 1. So we have u prime times v minus u times v prime. So u prime times v is going to be 50x minus 100 plus, or minus, u times v prime, which will be minus 50x, over v squared, which will be x minus 2 squared. The x becomes a 1 and the 50 goes away. So these two 50x's cancel. So this tells us that our first derivative, so this implies that dp dx is actually equal to minus 100 over x minus 2 squared. Now the question does tell us to show that your answer gives a minimum. And that means we either need to check values around whatever solution we find, or we need to do the second derivative. I'm going to do the second derivative, and I'm going to take that second derivative now, because I don't want to have to come back to it later. So we'll do this as another quotient rule. We have u and we have v. U is minus 100. V is x minus 2 squared. U prime is therefore 0. V prime is therefore 2 times x minus 2. So we have our second derivative, which is d squared p dx squared. This is u prime times v, which is 0, minus u times v prime, which is 200 times x minus 2, and this is divided by v squared, which is going to be x minus 2 to the 4. So we have the second derivative. We'll use this later, but we've just done it now while we were doing the derivatives. So now we need to let dp dx equals 0. This is our condition for finding mins and maxes. So dp dx was minus 100 over x minus 2 squared, minus 100 over x minus 2 squared equals 0. So this, we're missing a term here. This should be plus 1. We've got a plus 1 at the end. And the plus 1 would go away in the second derivative, so that's not an issue. So minus 100 over x minus 2 squared from both sides. Minus 100 over x minus 2 squared. So this gives us 1 is equal to 100 over x minus 2 squared. Multiply both sides by x minus 2 squared. This tells us that x minus 2 squared is equal to 100. Take the square root. This tells us that x minus 2 is equal to plus 2, or x minus 2 is equal to minus, sorry, not 2. It's equal to plus or minus 10, plus 10 or minus 10. Because we took a square root of a positive, it's giving us both of these numbers. So we add 2 to both sides in both cases. This tells us that x1, the first possible solution, is 12, and x2, the second possible solution, is minus 8. Now, of course, minus 8 is not possible. This is not a possible solution because x is one of the physical dimensions of a path, so it has to be positive, so you can immediately ignore this. So x is 12 is either a min or max. Now we are going to plug it into the second derivative, which we calculated up here, in order to work out if this is positive or negative or not. If this is positive, then it is a minimum. If it is negative, then it is a maximum. This is how second derivatives work. So we have x equals 12. So we'll just do this up here. Normally you do it lower down the page, but we can just work here. D squared p. This is just our test to determine whether this is actually a minimum. So this is 200 times 12 minus 2 over 12 minus 2 to the 4. Well, this is 200 times 10 over 10 to the 4. This is greater than 0. So therefore, x equals 12 is a min. So you have to do the confirmation in addition to finding the value. You can do the confirmation with a table of values. Table of values is quite common when you have questions like this because these formulas are a little bit difficult for some students. So you can just test the slopes, the derivatives around the point you find. If one goes down as it heads towards the point from the left and then goes up as it heads away from the point on the right, then it's a minimum. If it's the opposite, then it's a maximum. So you can do it that way. And the question, we have to be careful that we've actually answered the question. The question here says find the value of x such that the area of the concrete path is minimum. We were actually after x is 12. Sometimes these questions will ask you find the minimum area of the path. Then you will need to take the x is 12, plug it back in, and solve. Okay, so this is how we do this particular question. Now, in terms of the marking for the first part is pretty straightforward. I did it in a really long form, and so all of my working will just get 1 mark. Much shorter form of this first part is potentially going to be better in an exam, but whatever works, right? You get the 1 mark for this. For part B is worth a lot of marks, so this is worth 4 marks. You get 1 mark for finding an expression for the area of the path as a function of x. You get a 2nd mark for finding the derivative of that function. You get a 3rd mark for finding x is equal to 12, so identifying whatever the min or max point is, and then you get the final mark for providing the correct solution, x is 12, and confirming it using either table of values or second derivative test. So this is how we do question 24.